All right, hello pre-cal. This is notes lesson 1.8, inverse functions. Yesterday, or the previous lesson, we talked about composition of functions. And I said, is f of g of x the same as g of f of x? And it turns out that most of the time they are not equal. But they are equal when f and g are inverses of one another. And so these two compositions actually end up canceling each other out. They simplify down to x, which is kind of an interesting thing. And so we're going to talk about inverse functions today. They're very special functions that sort of just undo one another. We have two IXL assignments today. One is very quick and simple, and the other one's going to take a little bit more time. So graphically, an inverse. So this is the inverse notation. F inverse of x. And so this to the negative one really means inverse. And so you want to say the word inverse. You don't want to say f to the negative one power. Don't say that. It means inverse, and that's definitely notation you want to understand. So graphically, an inverse is a reflection about the line y equals x. So what I want to do is I want to show you this. The line y equals x, you can think it's like 1x plus 0. So it has a y-intercept at 0 and then a slope of 1 over 1. So up 1 over 1, up 1 over 1. So it's just this line right along the diagonal. And so this is the line of reflection of inverse functions, which is kind of interesting. So this is the line y equals x. What I want to do is I'm going to go ahead and plot these points. So 0, 0 is the point, negative 1, 3, and negative 4, 6 is right here. And this is a function, f of x. I'm going to go ahead and just sort of connect this in a nice smooth curve. I was imagining it was like a square root function. So this is our function y equals f of x. What we want to do is we want to actually see what happens if I were to reflect these points. And so to reflect means that we're going to go right straight perpendicular across this line of reflection. Well, 0, 0 is on the line of reflection, so it doesn't change. So this is going to be f inverse of x. So this is our inverse function. We're going to see what points they turn out to be when we reflect. And so I need to take this point, which is at negative 1, 3. And this point is going to go the same distance, right exactly perpendicular to this line. And then it comes out on the other side. Let's see. Right, exactly perpendicular. So hard to do. I had to do a whole class on this once. So it gets reflected and it pops out right here. So it reflects. That's the same distance here between the point and that line of reflection, and it's the same distance away from the line of reflection to its new point. And you'll notice this new point is actually at 3, negative 1. 3, negative 1. Well, what happened to those? Yeah, they just switched. Interesting. This point over here is at negative 4, 6. And if it goes, there we go. All right, we're going to pretend that didn't turn out to be the best point there. Okay, if it were to go exactly perpendicular to my line of reflection, then it pops out right here, which happens to be the point 6, negative 4. And so if I were to connect these, it looks something like this, kind of interesting. 6, negative 4. So what's happening here when we have this is y equals f inverse of x, all right? What's happening is these ordered pairs end up just swapping positions because they're reflecting over the line y equals x, which means X becomes Y and Y becomes X. They switch. What's also interesting is the domain and the range also switch. So on this first original function here, this purple function, this domain was everything to the left of 0. So this went from negative infinity all the way to 0. And the range was 0 and up. So the range went from 0 all the way to positive infinity. Well, when we look at our reflected function, it's kind of interesting. How far left does it go? Well, it starts at 0 and it's every x value to the right. So this domain starts at 0 and goes to positive infinity. And the range, the lowest value, this is going all the way down to negative infinity, and it's the highest value is 0. So it's going from negative infinity up to 0. So you'll notice the x's and y's switched, which causes the domain and range to also switch. The range, the y values became the domain values. The domain values become the range values. Kind of interesting. So all these things switch. The domain and range changes. The x's and y's swap. So whenever we think inverse, we think swap. All right, we're going to swap our x's and y's. And that's really, really good information. So we want to know, sometimes we know that a function must pass the vertical line test. A function, that's a special word, function, a function must pass the vertical line test. But we want to know what's required for an inverse to also be a function. We want to know if we can actually find an inverse that also happens to be a function. So an inverse, we want to know an inverse must pass what's called the horizontal line test. All right, and we'll talk more about that in just a minute. If we were to draw a horizontal line test, and our purple function here passes that horizontal line test, it just intersects one time. If we had a function, maybe that was like a sideways parabola, or rather, no, a parabola. Just kidding. If it happened to be a parabola, we have this parabola here. If we flip it, reflect it over the line y equals x, it turns into a sideways parabola, and that will no longer be a function. It would not pass the vertical line test. Kind of interesting, but we'll talk more about that. So using graphs, example 1, given the function, find the inverse value. So you'll notice they're giving me f of x in these graphs. It's important to know what we're looking at. They're giving me an original function. And so we want to know what would the inverse values be? And that's what we're talking about here. So you'll notice I have this little helpful information here. Normally, if our function, this is the original function, we have an x value and an output y value. Well, when they're using inverse notation, you can see what swapped here. They're just swapping the x and y's. So we can use, with this knowledge, we can use our original graph. We don't have to draw a new graph, but we could if we wanted to. I want to start down here. What is f evaluated at 0? So you'll notice this is the original function f here. Evaluated at 0 has an output of 4. And then the original function evaluated at -2 has an output of 7. Okay. And so they're going to ask you questions. Hey, if you thought about the inverse function evaluated at 7, what would the value be? Well, if we're referencing the original function, hey, that's actually a y value. So let's look and say, hey, referencing this graph that they gave us, if the y is 7, they want to know, hey, what's the x value? So, well, we already found that. That's -2. So you can see how they just swapped positions, okay? And then this is saying, hey, if our inverse was 4, if the y value was 4, what was rather the x value? Well, the x value was 0. And you can see that they just swapped positions. So kind of interesting. I'm not going to do that on this one. So this again is saying, hey, what's the inverse value? Which means, hey, I must be looking at a y value then. So -3 is down here. And it looks like that corresponding x value is 4. And what's the inverse? If I give you a 4, which must be an inverse, so that must be a y value of 4. Where's the y value of 4? We want to know what's the x value? 1. All right, so these are swapped. Just swapping. Swap, 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 swap. Okay, so now we do things algebraically. Example, oh, whoops, that should be example 2, I guess. There we go. Don't know how I missed that. That's okay. Example 2 is a 4-part sort of thing. Decide if f has an inverse. So in order to have an inverse, f must pass the horizontal line test. All right. So this first graph here, so for part A, this first graph is a line. All right, you could graph it on your calculator. In fact, I will. Go ahead and graph this equation, 3x plus 5. And we see a line. Okay, great. So this is a line, and we know it's a function. It passes the vertical line test. It also passes the horizontal line test. And since it passes the horizontal line test, it does have an inverse. Okay, so it does have an inverse because it passes the horizontal line test. We want to find the inverse function. So for part B, my favorite thing to do, my favorite phrase for finding inverses is swap and solve. Okay, so all we're doing when we find inverses is we're reflecting the function over the line y equals x. Well, that means our y and x need to swap positions. So we're going to trade these out. They're going to swap. We're going to say x equals 3y plus 5. So they trade places. And now we want to go ahead and solve for y. And that's the new y. We're basically just solving for the other guy. So we're going to go ahead and subtract 5 to get x minus 5 equals 3y. And to get y by itself, we're going to divide by 3. And so this x minus 5 over 3, which is a great answer. You can leave it like that. Perfect. I'm just going to change this to inverse notation. All right, so we got y by itself. So now I'm just going to replace that with, this is f inverse of x. Still in terms of x, but this is our inverse function. And we want to state the domain of f and f inverse. So this was a line. So since it was a line, the domain is from -infinity to +infinity, or x exists in the real numbers. And because it went forever to the left and forever to the right, let's check out this function. I'm going to go ahead and graph them on the same axis. So I'm going to add here. I'm going to put this in my calculator. I'm going to make sure I put parentheses. So x minus 5 divided by 3. And I should see a line that looks like it's been reflected over the line y equals x. Oh, it kind of does. This is not a square window, and it doesn't look like I have that option on this calculator. Maybe I do. Let's try zoom. Square, look at that. So I pressed zoom and then more, and I have square. You have that on your TI as well. So this is a square window, and you can imagine this line y equals x right here, and it's been sort of reflected over that line y equals x. We can check some points too. And so for instance, I could maybe use trace, and I see the point 0, 5 on this graph. Well, what point should be on this graph? We should see the point 5, 0. So I'm going to type in 5 and oops, and switch to my second function. So I arrow down. So my second function, 5, 0, is on the graph. So this point has the graph 5.50. So that's a great little double check to see if you did it right. You should have swapped ordered pairs, which is kind of cool. The domain, again, on this second function, this line goes forever to the left and forever to the right. So that domain is all real numbers, or x exists in the real number world, negative to positive infinity. Let's look at this. This is a cubic function. Oh my goodness, I keep hitting the wrong thing. Okay, I'm going to delete these. Okay, and we're going to start here looking at our original function. So the first thing is decide if f has an inverse. So I'm going to type it in, 3x cubed plus 1. And this is a cubic function. It's sort of a stretchy s. That's a nice little slide. And so we want to know, does it have an inverse? The question is, does it pass the horizontal line test? Absolutely, it passes the horizontal line test. So that means it has an inverse. F has an inverse function. An inverse, that is a function. We want to find the inverse function now. So for part B, we're going to swap and solve. So I have my equation y equals 3x cubed plus 1. Let's go ahead and talk about the domain of this function, since I'm going to do that. Our f function has a domain of all real numbers. It goes forever to the left and forever to the right. And so you might say x exists in the real numbers. I'm not sure what it's going to ask you on IXL. All right, so we want to swap and solve. So we're going to swap our x and our y, and then isolate the y. So I'm going to start by subtracting 1. So we have x minus 1 equals 3y cubed. I need to divide by 3. So we're going to divide by 3. Ooh. And then so we have x minus 1. I want to write this a little different way. This is dividing by 3 is the same as multiplying by 1/3. I'm doing that because I think they're going to ask you a very specific way to write this in IXL, and it's going to look like this. So we can divide by 3, or we can say multiply by 1/3. That's the same thing. And then how do we get y by itself? How do we get rid of a power of 3? We have to do a cube root of both sides. The cube root of the cube cancels out. And so we have the cube root of 1/3 x minus 1 equals y. And I'm going to go ahead and change that to function inverse notation. So I just took a second to look on IXL and see what they did. So it's kind of tricky how they want you to write your answers. This is an okay answer for me, but they might on there write your answer as ax plus b And this is not in that form. So, so to show you what to do there, this is 1/3 times the quantity x minus 5. So these two say the same thing. And then we can go ahead and we could distribute that 1/3. So 1/3 x minus 1/3 times -5 would be 5/3. So you could type it in that way. So you can see that there's a number in front of the x, and then there's another added value on the end. So you do want to kind of pay attention to that. They might have you do it on something like this as well, though they don't look that hard. So if I needed to not have parentheses, I could distribute 1/3 x minus 1/3. And so this would be an appropriate answer. So be careful when you're looking at the IXL. It's a little bit tricky. So let's go ahead and look at this cube root function. So I'm going to go back here. And I need to find my cube root button. On the TI, it's under the math menu. But here on the Casio, it's just a second function. So I can do, I think I need to type in the 3, and then I do the cube root. So 3 first, and that puts it in the little index in the radical there. Parenthesis, I'm going to have 1/3 x minus 1/3. Close those parentheses. Oh, nope. Look what it did there. It changed, and it says we're dividing by 3x. That's not what I want. We're going to put parentheses around the 1/3. Whoops. Oh, man. I want to get rid of this parenthesis. So I want to do 1/3 times x. Oops. Oh, my goodness. My fat fingers. I'm going to get rid of that parenthesis. And then I also need to subtract 1/3. So I'm going to put that in parentheses as well. Kind of tricky. You have to be a little bit careful there. Lots of parentheses going on, but I wanted a 1/3 as a fraction, so I put that around parentheses, and then minus the fraction 1/3. All right, let's see if that worked. Yes. This one really does look like, you can see that line of reflection right here. And when you think about the domain of this function, how far to the left and how far to the right does it go? Negative to positive infinity. So this is x exists in the real number land. Any real number will give you an output. Odd powers are always good. All right. Here we have some more complicated. I'm running out of time, so I'm going to try and do this quickly. This is a rational fractional function, and they look kind of funky, but we can still do them. If you're going to graph these in your calculator, you want to make sure you put parentheses around the numerator and denominator. So we're going to do x plus 5 divided by 3x minus 2. And we can graph that. And again, there's no vertical line here. That's an asymptote, but we have these little L shapes. And so graphically speaking, we have these little L shapes like this. And this, we want to know, does it have an inverse? Yes, it does. It passes the horizontal line test. These look like they're kind of horizontal lines themselves, but they're actually not. They are getting infinitely closer and closer and closer to 0, and they can do that forever. So it's not actually 0, it's actually 1/3. We want to talk about the domain of this function. So for the domain of this original function, remember, the denominator cannot equal 0. So I'm going to take my denominator and just solve. So it says I'm going to add 2 and then divide by 3. X cannot equal 2/3. And that's the domain. So that's an exclusion from the domain. Kind of nice to know that. And we want to go ahead. It passes the horizontal line test. So it does have an inverse. That's a function. Because it passes the horizontal line test. And now we want to go ahead and swap and solve. So my original function was y equals x plus 5 over 3x minus 2. I'm going to trade my x's and y's. So we're going to have x equals y plus 5 over 3y minus 2. This is a very complicated type to solve. How do you do this? The first step, we're going to cross multiply. So we're going to multiply. X times 3y minus 2 equals 1 times y plus 5. We're going to go ahead and distribute. So I'm going to get 3xy minus 2x equals, in this case, y plus 5. And then we want to collect our y's on one side. So I'm going to go ahead and move this y over to the left-hand side. And I also don't need this term. I'm going to move him to the right side. So I have 3xy. I have to subtract the y. To take this negative 2x, we're going to add it to the right side. So I just traded some terms around there, but we want to collect the y's because I'm interested in solving for y. And then they have a greatest common factor. We want to factor out the y. So I'm going to take that y out. If I take my y out, what's left behind? The 3x and the negative 1. Remember, you can always check by distributing. And then we just need to divide to get y by itself. I'm going to divide by the whole group, 3x minus 1. So I have f inverse of x equals 2x plus 5 over 3x minus 1. And this is the form that IXL wants it in. So this is a great answer. And what's the domain of this function? Well, again, it has a denominator. 3x minus 1 is not allowed to be 0, which means x is not allowed to be 1/3. So there is the domain of the inverse function. All right. You could verify graphically, but it's kind of just confusing. Last one here, and I've got 3 minutes. So square root of x is a tricky one. So square root of x, and then we have plus 3. You notice I don't need parentheses on that. So this is a square root swoop that's been shifted up 3 units. 1, 2, 3. And so it is a square root swoop. It does have an inverse. It passes the horizontal line test. Therefore, inverse function. It's an inverse that is also a function. But we have to be pretty careful. The domain on this function is farthest left here. We start at 0 and it goes all the way to infinity. So you would say x is greater than or equal to 0 for the domain. We want to go ahead and figure out the inverse. So we're going to swap. This is the same as y. So I'm going to say x equals the square root of y plus 3. And then we can solve for y. So I'm going to subtract 3. And then how do we get y by itself? Well, to cancel out a square root, we have to square both sides. The square root and the square cancel out. And so I get x minus 3 quantity squared equals our inverse function. It equals y. I think this is how they want it in IXL, but we do have to be careful because this domain cannot be. This is a parabola. And you can see here we only have half a parabola. Well, I'm going to go back to, I'm going to go exit and go back to my graph here. If I graph this, this is not really an inverse function. You can see we only want half of this thing. All right, we only want half of this parabola. We don't want the whole thing. We only want from 3 on. All right, so here, let's talk about the range of this function. The range of our original function was from 3 to infinity, or y was greater than or equal to 3. Well, remember we talked about how domain and range swap. So if we knew the range was y values greater than 3, then that's the domain here. X values greater than or equal to 3. So remember, when we're swapping our x's and y's, our domain and range swap also, and that's a really good hint. Okay, so keep that in mind. That's pretty tricky, and you'll have a couple of those. Folks, have a good practice.